Okay. Hey, everybody. So nice to see you all back here. It's nice to have Chris Blair with us today virtually. Hi, Chris. And Chris will tell us something about generalized U-dual solutions and supergravity. Please, Chris, go ahead.
Okay, thank you. So first I should start with a very big thanks to the organizers, not just for inviting me, but for accommodating it so that I can speak to you from afar today, and for already putting in the effort of making everything available online. So it's a big effort, and I appreciate it. And I'm sorry I made it more difficult, and I'm not there in person. But I think hopefully I can give the same sort of talk I would have given anyway, and hopefully it will be clear and no technical difficulties. So I'm going to talk about three, well, I'm going to sort of summarize the results of three papers from the last couple of years, two with my PhD student Sophia here in Brussels, and one also with Dan, who's at the conference. And the topic is about so-called generalized U-duality, and I'll try to explain what this idea is. So I'll start with a very anodyne statement, which is that in this conference and in string and M theory in general, duality is an important central connecting principle that allows us to explore different parts of the theory, find new solutions, and draw links between different topics and different behaviors. And my talk today is really going to focus on duality as something of interest in itself. There'll be little bits of mentions of deformations and a much less mention of integrability. But there will be things that I think will be of interest and which will speak to the other topics of the conference. So in particular, the type of duality which I'm going to talk about is masquerading under the name of generalized dualities. And so the precise sense in which it's a generalization of, let's say, standard string theory dualities will become clearer in a couple of slides, hopefully. But I talk a little bit about the motivation for studying this topic in general. So generalized T-duality will probably be more familiar to people in the audience and will be the subject of other talks at this workshop. And it's of interest as a mechanism that generates new supergravity solutions. Non-abelian T-duality is an example of a generalized T-duality, and it's led to a lot of work in constructing new interesting holographic backgrounds. And generalized T-dualities have a lot of links to integrable deformations of worldsheet models and backgrounds leading to these integrable theories. So it's kind of a tool that you can use to explore and find new interesting string theory backgrounds. From a more mathematical point of view, perhaps something that's also of interest to me and maybe coming from this doubled and exceptional geometry community is that to make the structures that appear in generalized T-duality clearer, you find out that you have to emphasize the role of underlying doubled geometric or doubled algebraic symmetry structures. So these are dualities that on the face of it may seem a bit obscure when you first meet them, but which look cleaner from a different perspective, which uses these powerful duality symmetric structures. So generalized T-duality is pretty well established and has been used extensively. So T-duality is a famous symmetry of string theory in 10 dimensions. But we know that there's this non-perturbative extension, which is U-duality, which then applies also as a duality in M theory in 11 dimensions as well. So recently there's been some work about trying to come up with definitions or frameworks in which you could realize generalizations of the U-duality symmetry that look like these known forms of generalized T-duality. So why would you want to do that? The first reason I came up with is just to see if it exists. Often structures in string theory have some nice lift or generalization to structures in M theory. So first of all, we want to know if you can actually define other sorts of generalized dualities that would apply in that context. And then, okay, assuming it does exist and is useful, what you want to do is then try to repeat the successes of generalized T-duality as a probe of the sorts of, as a probe of interesting new supergravity solutions in both 10 and 11 dimensions, and then to see if you can find solutions with properties related to holography or interesting integrable or otherwise deformations, to see if you can find solutions with similar properties in 11 rather than 10 dimensions. And then again, from maybe my personal perspective, it's also interesting because the sort of common feature that I'll leverage to define generalized U-duality is to look at these sort of underlying doubled or exceptional geometric symmetry structures, which pop up and new structures appear that are sort of interesting to study as features of special supergravity solutions that you can then use to define notions of generalized U-duality. So that's the sort of slightly big picture motivation. And the actual result, which will come out of this motivation in this talk, is the following. It's going to be what I'll describe as an example of a generalized U-duality, and it will be a sort of elaboration of non-abelian T-duality, which is perhaps the most well-known generalized T-duality. So non-abelian T-duality is a duality transformation between a space that has non-abelian isometries to a dual background that has fewer isometries than the space you started off with. So here's a sort of standard example. You start off with the three-sphere, regarded as the group manifold SU2. You do a dualization procedure and you get a non-abelian T-dual background that in a certain sense has abelian non-isometries, meaning that if you tried to look at the commuting algebra of the would-be algebra of translations in this background, translations are not a symmetry, you don't have a translational isometry, but the isometry is broken in a very specific way thanks to the presence of some dual Lie algebraic structure. So there's some rigid symmetry structure underlying the form of this dual background, which is inherited from the non-abelian symmetry you started with. And I'm going to describe an elaboration, which is a similar map, but in the context of an 11-dimensional, something that will generate a solution of 11-dimensional rather than 10-dimensional supergravity. And it's actually going to be a map, not from a space with non-abelian isometries, but from a three-sphere in type 2a with NS and S flux to an 11-dimensional background, which will have a similar appearance to the non-abelian T-dual background that you get from non-abelian T-duality, but where the sort of rigid algebraic structure that's preventing you from having certain translational isometries is not connected to a Lie algebra, but to a tree algebra structure. And this is a generalization of this non-abelian T-dual chain, but it's slightly different in spirit. So a little piece of intuition from regular T and U duality is that T-duality can swap between 2b and 2a. So a single T-duality does that, or any odd number of T-dualities. Whereas U-duality sort of keeps you in 11 dimensions, or keeps you in 2a, or keeps you in 2b. It can only reduce to an even number of T-dualities. So even though on the right-hand side I have some structure similar to the non-abelian T-dual, I don't quite see non-abelian isometries playing the same role. And what I think I'm really going to describe to you is a generalization of a T-duality chain where if I take this three-sphere and I do a T-duality on the hop fiber, I get a space which is S2 times S1 with flux. And we should really think of the generalized U-duality I described to you today as generalizing a map from this S2 times S1 with flux to this non-abelian T-dual background, skipping this middle step. And this is what's going to get uplifted to this U-duality elaboration. So I'll explain later on why I decide to sort of, I don't focus on the non-abelian isometries so much, I focus on the structure of the background that appears on the very right-hand side of these chains. And okay, the motivation for doing this I will come to later, but the upshot is this mechanism is a solution generating mechanism between 10-dimensional and 11-dimensional supergravity. And I claim it gives interesting 11D backgrounds. So in a a paper this March, we studied some examples. So I have a duality, or a set of rules for taking a solution of 10-dimensional 2A supergravity of the form M7 times a 3-sphere. I chop off the 3-sphere and I replace it with some new 4-dimensional space by a generalized U-duality transformation, and I get a new 11D solution. So an example would be if this spectator 7-dimensional manifold is ADS3 times T4, in which case I can view my initial solution as a near horizon of a string 5-brane intersection. Then I get an 11-dimensional ADS3 solution, which actually turned out not to be a new solution, but it fits into a class of ADS3 solutions that has been obtained a couple of years ago. And what's interesting about this fact is that the solutions my procedure generates are all local solutions. You don't know the global range of the coordinates that you write down the solution in. But these ADS3 solutions that have been already studied have there's a prescription to give them a global completion using ideas from holography that are very similar to what appears when you study non-abelian T-duality. So this new 11D solution, which shares features with non-abelian T-duality, also shares some of the features of the holography and global issues of non-abelian T-dual solutions. Then in this paper, we also could consider the case where this initial solution is this string 5-brane intersection. And you can look at just the 5-brane near horizon region. In fact, we always have to do that. And then this more full solution can be viewed as a particular deformation of this ADS3 limit. It's a kind of weird deformation. It's what I called a 6-vector deformation. So it's actually a deformation by an element of the U-duality group, but not acting on isometric directions only. It acts on both 2 isometric directions and the 4 special directions of this new space, which are not isometries. So it's an unusual deformation, and it takes you basically away from the near horizon region of the string to this solution. It's in fact inherited from TST or bivector deformation of the original ADS3 times T4 solution in 2A. And I just mentioned that has a holographic interpretation has been dual to the TT bar deformation, version of the TT bar deformation of the dual C of T. So that's an interesting link there, about which I will not be able to say very much in this talk, but I mentioned it as it should be interesting. And in fact, a more general statement about these deformations is that if I take this solution generating mechanism and I suppose that the spectator 7-dimensional spacetime has 2 commuting isometries, then in string theory I can consider doing particular T-duality valued deformations, such as TST deformations. And any such deformation is inherited by the new 11-dimensional solution as what I call, again, a non-isometric U-duality, particular E6 U-duality valued deformation of the 11-dimensional solution, which acts in both isometric and non-isometric directions. And this seems to me to be an example of a new class of potential deformations you can apply to particular solutions in supergravity, those that come out of these generalized duality constructions, where you're doing something that's like a U-duality, but you're not relying on isometries, which you should normally do to apply U-duality. So that basically completes, I think, what I would call the gong show version of this talk. So a little summary of the motivation and a little summary of the results. So if you don't like listening to remote talks at physical conferences, you can now switch off and go for a walk. I can't really see you, so I don't mind. And so what I'll now do is I'll sort of go back and elaborate on the introduction and the motivation, and try to be a bit more clear about what I mean by generalized U-duality, or how I could formulate generalized duality in general. And after I'm doing that, I'll talk about these results again in a slightly more technical way. But I just leave a little pause in case there are any questions so far. Okay. And so now I'm going to go back to the beginning or the motivation and start thinking about duality. So the generalized dualities I'm talking about are generalizations of this, of the classic string theory or M-theory dualities, which are usually phrased as a relationship between two different theories on different backgrounds. So theory 1 on some spacetime m times x1 is dual to theory 2 on space m times x2. And the classic T and U dualities, these apply when the spaces x1 and x2 are tori or have abelian isometries. And this is a large part of the duality web of string theory uses these dualities to relate type 2 on a circle with type 2 on a dual circle, and so on and so forth. So one question is, okay, how can you generalize this away from, let's say, away from tori? And I'm interested in generalizing in a sort of systematic way. So you can certainly think of many examples involving spaces like K3 or so on. But I want to look for things that are similar in spirit to T and U dualities, where I have some prescription to identify classes of spaces x1, which lead to classes of spaces x2. And I have some nice set of transformation rules between them, akin to the Bush rules in T duality, for instance. So given that the basic requirement for T duality or U duality is that you have some abelian isometry, a starting point would be to say, well, what happens if I apply duality in a situation where I have isometries, but they're non-abelian? And I can most easily do this in T duality, because then I can use the worldsheet sigma model to apply such dualization procedures. And this was done long ago in the case of non-abelian T duality, where you carry out a similar dualization procedure as you do for ordinary T duality, but in a background with non-abelian isometries. And the interesting feature is that you get a dual background, but you kind of end up with a dual background that's not of the same type as you started with. So you end up with a background generically with fewer isometries than the initial background with non-abelian isometries. If you start with a group manifold, you end up with something that's not a group manifold. So what this tells you is that isometries are somehow not the essential ingredient in whatever class of generalized dualities this is beginning to construct. And this is made really manifest when you then turn to what turns out to be a more general case of generalized T dualities, which is the Poissonly T duality. And this relates pairs of dual backgrounds which are specified by an underlying symmetry structure that's not actually a symmetry of the spacetime itself. So there's some underlying Poissonly group, which is just an ordinary group, but with a little bit of extra structure in the sense that you can define a geometric object called a bivector. So something with two vector indices on the group obeying certain compatibility conditions. And there's a particular relationship between the spacetime geometry and the data on this group. But the action of the group is not an isometry as long as this bivector is non-zero. So there's some additional information contained in this extra object related to a dual Lie algebraic structure. And this appears in this more general Poissonly T duality, which gives you pairs of classically canonically equivalent or dual sigma models. But there's no real role being played by a space-time isometry, but there is a very important role being played by a more intricate and somewhat more hidden symmetry structure. So that's a starting point for studying generalized T duality. Then if you wanted to ask similar questions in the U-duality case, well, you can't rely on worldsheet sigma model approaches. This is because whereas T-duality is perturbative symmetry, relating strings to strings, U-duality is non-perturbative, it relates strings to branes. So already you need, well, additional angles, or you need additional evidence to understand U-duality and its relationship to T-duality. And the generalized T-dualities, which I described in the last slide, it's already a bit unclear what happens when you want to extend to the full quantum string theory. You get a little bit less information from the worldsheet theory than you get in in the case of T-duality, where everything is sort of under control at the quantum level. So for U-duality, you don't even have a world sheet or world volume model that you can control. So what's safest to do is what I'm going to do next is restrict to supergravity. You can formulate these generalized T-duality transformations at the level of supergravity. And then it's clear how to generalize to 11-dimensional supergravity and interpret in terms of U-duality or generalized U-duality. So in the supergravity setup, and the justification for this restriction is also that, well, this is sort of where these transformations are known to be useful as solution generating mechanisms. So even if I can't answer questions about whether it's an honest or full duality in string theory, M theory, at least I'm going to get something I can use pragmatically in supergravity, which is nice to have as well. So in the supergravity setting, I'm going to slightly rephrase my statements about duality. So previously I said, oh, well, theory 1 on space x1 is dual to theory 2 on space x2. And the word on is doing a lot of heavy lifting in that statement. So another way of describing the relationship between two theories which are dual, which is often used in string theory as well, is to think about it in terms of a dimensional reduction. So if I dimensionally reduce theory 1 on x1, and I dimensionally reduce theory 2 on x2, these theories will be dual if what I get at the bottom is a common theory defined in this common spectator spacetime now. So for instance, type 2a string theory on a dimensionally reduced on a circle, or a type 2a supergravity dimensionally reduced on a circle, gives you the common 9-dimensional maximal supergravity, and you also get that from a dimensional reduction of type 2b in a circle. And then you have to do some field relabeling in 9 dimensions to relate these two reductions, and that's equivalent to doing duality in 10 dimensions. So all ordinary string dualities in supergravity, I can think of them in this way, in terms of a reduction to a common theory from two slightly different starting points. And so my definition of duality can be this statement, and this is now a slightly weaker statement, that I do some reduction or truncation of the two theories, I get the same theory. And that's useful in supergravity if it gives me a way to take a solution of the first theory, reduce it to a solution of the common theory, and then invert the reduction procedure by uplifting it to a solution of the second theory. So I can do this if I know I can map solutions from higher dimensions to lower dimensions, i.e. if my reduction is a consistent truncation. So I sort of have a commutative diagram of sorts where, okay, my solutions are dual if I can use this procedure to go from one to the other. And once I've done this, I can sort of forget about the lower dimensional theory. I can just write down what were the rules to take the solution of the first form, m times x1, to a solution of the second form, m times x2. And that uses as a technical tool the common theory in lower dimensions, but at the end of the day, I can just say, okay, here are the rules to go from solution 1 to solution 2. So for this talk, this is kind of what I have in mind as my definition of generalized duality. It's kind of broad, but I'd say it's a very weak notion of duality. So this is certainly a solution generating mechanism. If I have two backgrounds and I can consistently truncate them to the same solution in lower dimensions of the same lower dimensional theory, then I have a map between the solutions, and I can regard that as a solution generating mechanism or as a generalized duality. This certainly includes known dualities and known generalized dualities as examples. Let me say at this point that then if you view this just as a solution generating mechanism, maybe you object to calling it generalized duality. Maybe duality is a stronger word, but okay. That's kind of a question of language. So as a first step towards formulating these dualities, at least I'm setting up this solution generating mechanism. So then also, what I described is also very general. That means it needs to be useful as well as general. So for truly to be useful, you need a recipe for identifying when you have this setup with pairs of dual backgrounds. And this sort of recipe is what sort of comes with known formulations of generalized T-duality. It's why they're useful. It's quite clear when they can be applied. This general definition is much more general, but you have to sort of then be precise about what sort of rules are in place to ensure that you can do this mechanism. Something which helps here is the question of how do you identify, given some upstairs space and you do this truncation, what is the lower dimensional common theory? So in the examples of generalized dualities that I described, the lower dimensional common theory will always be a lower dimensional gauge supergravity. And so this is some extension of the ordinary supergravity where you have some local non-abelian symmetry with so-called gaugings or structure constants, which I denote by capital F. And the algebra of these structure constants will pop up again, or is also going to be some special algebras that will underlie known notions and new notions of generalized duality. So this is the framework in which I try to set up now some definition of generalized duality. And so what I try to focus on is with this idea in mind of having different backgrounds that reduce to solutions of a lower dimensional theory, the same solutions. What's the recipe for knowing when you can do that? So I'll start by describing this recipe for the case of Poisson-Lie T-duality, which is a very well-known generalized T-duality. So I alluded to this earlier. The data you need to specify this duality is a Poisson-Lie group, so some group manifold in which I have some bivector pi. So I have some compatibility conditions between the group and the bivector. And so I write down some differential equations here. So these L's are the left invariant one forms on the group. So L is trace G inverse DG, or the other way around. They obey this Maurer-Cartan equation. And this bivector is meant to obey some condition like this. So in the equation here on the left, you have the structure constants for the Lie algebra of the group. And then the derivative of the bivector involves those structure constants, but also involves dual structure constants of tilde, which is some extra structure associated to this Poisson-Lie group. And there's different recipes for constructing the space-time background that admits this Poisson-Lie T-duality, or that is built using this data. So instead of giving you the explicit formulae, which are not illuminating on their own, I'll give you a less explicit formula, which is more illuminating for my purposes. And this is the prescription to embed these Poisson-Lie backgrounds in terms of generalized geometry. So here I want to describe the background in terms of the metric and the B field in 10 dimensions, or in some d-dimensional subspace of my full solution. And a useful object with which to describe the metric and the B field together is this 2D times 2D matrix, which I would call a generalized metric. And this is some nonlinear combination of G and B that has particular nice properties under ordinary T-duality and under dimensional reductions. But the particular form of the metric and B field for a background which emits Poisson-Lie T-duality follow from a factorization of this matrix, in which all of the data about this Poisson-Lie group factorizes out in this matrix E, which I should think of as some sort of generalized Vielbein for this combination of G and B, and some constant flat metric, which I denote H naught. And so appearing in this matrix E are my left invariant one forms L, their dual vectors V, and this bivector pi. And if you inverse this relationship with H naught, some arbitrary matrix constants obeying some ODD condition, you can extract explicit expressions for G and B in terms of L and pi, and these constants. And there's a special property of this factorization, which is important, which is that if I'm doing things in generalized geometry, I can formulate, okay, first of all, I can formulate a notion of a generalized vector, which is a pair here of a vector and a covector. And there's a generalization of the Lie derivative acting on such pairs called the generalized Lie derivative. And the inverse of this generalized Vielbein gives a basis for generalized vectors, which obey a sort of parallelization condition in which a particular set of structure constants appear related to the structure constants of the related to the structure constants I mentioned on the previous slide, which will control the form of the lower dimensional theory and which play a role in determining the allowed dualities in this setup. And so this condition generalizes, if I was just dealing with an ordinary group, these vectors VA would obey a parallelization condition that they're under the Lie derivative, they would form the Lie algebra of the Poisson group. But here I don't only have a group structure, I also have this bivector structure, and I guess a bigger 2D dimensional algebra associated to these backgrounds. So the generalized geometry, if you formulate it in terms of this particular set of variables, sees both F and F tilde, whereas if I structure this as a group manifold, I would just see F. So I have to work with additional structures. And the algebra that appears is known as the Drinfeld double algebra, and it incorporates both these structure constants F and these dual structure constants F tilde on the same footing. And this has some special properties, namely that there are two subalgebras. So these structure constants F give you a subalgebra, and the structure constants F tilde give you another subalgebra. And the statement of Poisson T duality at the algebraic level is just that you can swap this algebra T's with this algebra for the T tildes. It's equivalent to swapping F and F tilde. And then to generate a new background, you can go back to the differential conditions I wrote down on the previous slide and solve them with F and F tilde replaced, swapped for some new group data and a new bivector. And then you can build the same objects in generalized geometry, and you build a new background, new metric, and be filled in this way. And that creates the rules for Poisson T duality. So the duality has a sort of geometric incarnation, which is slightly complicated, but this geometry encodes a particular algebra via the generalized geometric realization, and is also an algebraic incarnation of the duality as just exchanging subalgebras with special properties from one another. Now, a special case of this Poisson T duality is non-abelian T duality. So I focus on this a little bit because I want to specifically generalize this. So in the non-abelian T dual case, you start off with an ordinary group manifold, let's say. So that's a situation where I can forget about this confusing extra structure, the bivector, and I just have some space with some non-abelian isometries specified by non-zero structure constants F, A, B, C. But these dual structure constants are not present. And then the duality that I'm telling you exists. This swaps F and F tilde. And it gives you a structure then where your Poisson group is trivial. It's abelian because your F's are 0. But there is a non-trivial bivector because you have these dual structure constants non-zero. And the condition that d pi is F tilde can be solved by taking your bivector to be linear in some new set of coordinates x, which are the coordinates on your new space. So a specific example is this example of S3 viewed as SC2. So if my initial metric on this S3 is just given by these left invariant forms, L tensor L, the non-abelian T-dual space comes out with if you go through the steps or figure out what these generalized metrics tell you about the background, it comes out as this three-dimensional background here. So this space then is not a group manifold in itself. It has a complicated structure, but it has quite a simple presentation as a Poisson group. It's defined by a linear bivector. And again, this space does not have the isometries that you started off with, and it has a slightly curious structure. And one thing that's important is that both the metric and the B field get turned. So what I then want to do is think about what sort of versions of this duality could exist, not in string theory, but in an 11-dimensional setting with U-duality. And so in the Poisson-Lie setting, what was important was that there was this very specific group structure that then had a nice embedding into this generalized geometric construction from which you could extract the background and see things like this underlying algebra. And so there was a proposal in 2019, at the end of 2019, for what would be an analogous group structure that could control a version of Poisson-Lie U-duality. So the intuition here is that in 10 dimensions, you have a metric and a B field, which is a 2-form. And then in 11-dimensional supergravity, instead of having a 2-form, which couples to strings, you have a 3-form, which couples to membranes. And the idea of this generalization is basically to add an extra index to anything that is related to the 2-form. So the proposal of these people was that you should consider a generalization of a Poisson-Lie group where you don't have a bivector, but a trivector. The idea is that the bivector is in a certain sense linked to having a 2-form in your spacetime theory, and the trivector is now linked to having a 3-form in your spacetime theory. And you can then assume that the group is still a group, so you have this sort of Mara-Cartan identity, but then you want your derivative of this trivector object to involve some additional algebraic structures, and just by adding an index to what you had before, the idea is that the derivative of the trivector gives you some structure constant here, F tilde ABCD, with 3 antisymmetric indices upstairs. So this is not a set of Lie algebra structure constants, but it's can be viewed as a structure constants for a bracket of 3 elements. So that would be what's known as a 3 algebra. And there's a technical construction. Here I'm focusing on the 4-dimensional case, just for simplicity. The details depend on dimension, unlike in the Poisson-Lie case, Poisson-Lie T-duality case. So there's a construction known as exceptional generalized geometry, which captures the backgrounds that appear in 11-dimensional supergravity with a metric G and a 3-form, which they call C. The representation theory related to the exceptional groups is a little bit more complicated. I don't really want to go into it. But the idea is that you can construct combinations of the metric and the 3-form that give you quantities which behave nicely under U-duality. And for these special Poisson-Lie U-duality backgrounds, they factorize in a similar way, where you have some factorization where all the information about this underlying Poisson-Lie group appears in some set of generalized field lines, which obey an algebra under some natural Lie derivative, generalized Lie derivative. And this algebra is then inherited from basically from these conditions on D of L and D of pi. And so this is mimicking the structure of generalized T-duality. You get some underlying algebra from this generalized parallelization, which is termed an exceptional dreamfield algebra. It's not necessarily a Lie algebra. It involves these structure constants F and this 3 algebra structure constants F tilde in a complicated way. So the generators here are, there's a Lie subalgebra generated by these TAs. The indices A, B, and these T tildes are antisymmetric. So in this is a 4D example. There are 4 TAs and there are 6 T tilde ABs antisymmetric. That's the right representation structure to get an antisymmetric representation of the correct U-duality group, which is SL5 in this case. So you can check closure conditions or the compatibility conditions. You get things like the analogy of the Jacobi identity for the three algebra structure constants. What you also want to do is you want a rule to specify when you have a subalgebra. And your previous dualities in the Poisson T-duality case were about taking two different subalgebras of this sort of structure and then reading off what the dual background should be, knowing what the structure constants look like in these different representations based on different subalgebras. And so you can play a similar game here. The main difference with respect to the T-duality case is that there's no obvious symmetry between these F structure constants and these F tilde structure constants. The previous generalized T-duality was swapping F and F tilde. Here you can't do that because, well, one is a Lie algebra structure constant and the other is not, and the dimensions just don't add up. So if you like, this structure is the generalization of the structures that existed before, but it's a little bit more rigid and it might not allow you to find exactly the same types of duality as beforehand. But nonetheless, it's interesting to explore because it allows you to sort of focus on sort of the backgrounds in 11 dimensions or in M theory that would share certain properties with the solutions that appear in generalized T-duality. So, for example, one could look at, okay, what are the sort of solutions that appeared in generalized T-duality after doing non-abelian T-duality? These are characterized by having some trivial structure constants F, but they had non-trivial dual structure constants F tilde. And so if you focus on that case, you should get something similar. So these are solutions which somehow are linked to the presence of a underlying three algebra symmetry. So we call these three algebra geometries. An interesting example is to directly generalize what you get from the non-abelian T-dual of S3 or SE2. So that would just be the case where you have this F tilde ABCD is just the four-dimensional alternating symbol. And you can solve the conditions for the Poisson-Lie group by taking this trivector object to be epsilon ABCD times some new set of four-dimensional coordinates XD. And that gives something which feels like a generalization of non-abelian T-duality to M theory. But okay, you have to actually construct explicit examples of backgrounds of this type. And then you actually have to ask, are they actually generalized dual in the sense I described before to something? Otherwise, you're just describing isolated solutions with some nice algebraic story, but there's no duality. So the way to do this is to exploit the full algebra that you get out of this construction. This turns out to be a Lie algebra known as CSO 401, or more familiarly as ISO 4, which is to say the Euclidean version of the Poincare group. So it's four-dimensional Euclidean rotations and translations. And okay, so the first thing you can check in this algebra within this Poisson-Lie U-duality proposal, is there another description of the same algebra which has the same structure and which has another dual subalgebra meeting certain conditions that allow you to immediately apply a recipe for duality based again on having a Poisson-Lie group with a different group and a different trivector. And that turned out not to be possible. Unlike in the Poisson-Lie T-duality case, there just were no other examples after classifying all possible subalgebras. None of them fit into the framework in the same way. That's kind of connected to the point I made at the start about this not exactly being a generalization of non-abelian T-duality itself. It tells you have to go slightly outside the framework. You have to relax some of the conditions about identifying the dual subalgebra. Alternatively, you can just use the fact that there's this direct link between this big exceptional Drinfeld algebra and the algebra that will appear in the low-dimensional theory that I will truncate to. So this generalized geometric formulation guarantees that you get a nice consistent truncation, and in this case it'll be to ISO 4 gauge supergravity in 7 dimensions. So this is what we're able to use to build new solutions. So we've identified on the right-hand side, we identified a particular prescription for building an 11-dimensional background that uses this trivector, which involves some free algebra structure constant. And this thing feels like it should be the right-hand side of a duality, like a non-abelian U-duality. And we know that this can be, backgrounds of this form can be reduced to a low-dimensional gauge supergravity with a particular gauging. And it's already known how to do these consistent truncations from a different starting point, completely different background, which is to take 10-dimensional 2A supergravity on a tree sphere with flux. So there's some horribly complicated ansatz in the literature that takes a 10D theory here with a particular form, 10D solution with a particular tree sphere factor, truncates it to a solution of a 7-dimensional theory. And then our investigations of generalized U-duality give us an alternative truncation from a different background in 11 dimensions to the same point. And so by my weak idea of generalized U-duality, I can relate solutions of this 10D theory on S3 to new solutions of 11D supergravity on this new geometry that is somehow specified by this underlying tree algebra structure and some underlying notion of a Poisson Lie group with a trivector. So this means we get something actually useful. We can get a way to generate new supergravity solutions and then explore their properties. So an example which we looked at is on the left-hand side to start off with this string and near horizon 5-brane solution. So this involves some 10D metric like this. There's a tree form of this form, the important point being that there's some flux of the tree form on the sphere that's needed for this ansatz to work. And we can do this truncation and uplift procedure using tools from generalized geometry to get a new 11D solution, which I write in all its glory here. So the parts highlighted in blue, if you like, these are the bits that directly resemble the non-abelian T-dual solution of S3. So you have this sort of 1 plus xx factor in the metric, and this 1 over, in this case, some function plus x squared. And then here in the brackets, we have some components of the 11-dimensional tree form instead of the 10-dimensional 2 form. So you have, again, the same structure where you have basically hereCijk is epsilon tensor times x. In the non-abelian T-dual case, you had the 2 form B was epsilon ijk times x in 3 dimensions. This is a 4-dimensional generalization. And then there's a lot of extra conformal factors and things which are kind of required by the condition that this be an 11-dimensional solution. So, okay, it's a proof of concept. This is a brand new solution of supergravity. So what can we say about it? And it comes from a brane intersection, which is kind of nice. So one important comment is that, first of all, it's a local solution. We don't know anything about the range of those x's. We can find a global prescription to complete it by looking in the ADS limit, which corresponds to r squared f1 is 1. So there's a limit in which the solution takes some conformal factor times ADS3 times T4 times a radial coordinate, which you introduce times some sort of warp sphere factor. This, as I advertised at the start, this is actually can be fitted into a class of M-theory ADS3 solutions obtained previously. So these ADS3 solutions have a similar form. They're specified by a coordinate var rho, and these functions that appear are linear functions of rho, but actually they are required only to be piecewise linear. And then this rho takes values in some interval, and at different points inside the interval, the slope of these functions can change. And this is known to have some holographic dual to some quiver field theory. And if you know about the holographic duals to non-abelian T-dual solutions. This is very similar and in some senses directly inspired by those constructions. And interestingly, our solution can be fitted into, let's say, the first subinterval of these general class of solutions with some particular coordinate redefinition and choice of these functions. And this is sort of exactly analogous to what happens to non-abelian T-dual solutions. And if these solutions have not already been found, having been inspired by non-abelian T-duality, this non-abelian U-duality elaboration could have instigated the same work. So it has very similar features to what you get from non-abelian T-duality, and so you can play the same games. So that's nice, and it kind of shows there's some common structure between these 10D solutions with linear bivector in non-abelian T-duality and these new 11D solutions with a linear trivector. They somehow both allow for ADS solutions with these sort of similar stories for the holographic duals. But we have a little bit more than the ADS limit. So we have this full solution, which came from let's say, we're not in the near horizon limit of the original fundamental string part of the solution. And I make this claim that the full solution can be viewed as a deformation of the ADS limit, and the deformation parameter, I say, is a 6 vector, which I will explain in a moment. So I've written up the solution in spherical coordinates. To guide the eye, I introduce a deformation parameter lambda by rescaling some of the coordinates, but it's more of an on-off parameter. I can always remove it by rescaling if it's non-zero. But it kind of shows that this thing looks a bit like a deformation or a U-duality transformation of something else. So lambda equals 0 is ADS, is the ADS limit I talked about before. You'll notice I've written the 3 form and its dual 6 form. There's a reason for that. So what one finds, what one can show is that lambda not equals 0 is a U-duality transformation, if you like, an E6 valued U-duality transformation. So that means U-duality acting in 6 directions of the lambda equals 0 solution. What's weird is that this U-duality transformation acts on the T and Z coordinates, which are isometries, and it acts on the new 4-dimensional coordinates, which are not isometries. So it's quite a non-standard deformation by a U-duality parameter. There's a story then about what do E6 U-duality transformations look like, and some U-duality transformations look like shifts of the actual physical 3 form or its dual 6 form, but then non-geometric U-dualities have a geometric interpretation as 3 vectors or 6 vectors, and this particular U-duality that shows up here is a 6-vector deformation of the lambda equals 0 vector. So this is an unusual feature. It's quite an involved transformation. The last thing I'll say is that this happens really because it's a feature of the original solution. So it's some property which is inherited by the new 11D solution, but it's inherited in a way that brings in these non-isometric directions that make up the new 4D part of the geometry. So what is interesting is that in the original fundamental string NS5 grain solution, there's a similar story where the ADS limit can be viewed as, you can view the full solution as being a TST or O22 bivector transformation acting on the ADS limit, which is a sort of an honest T-duality, and at least in the sense that it's along abelian directions. What's interesting about this deformation is that it's been identified as being dual to a single trace version of the TT bar deformation of the dual C of T2. So then this much more complicated looking 6-vector transformation may be doing something similar to the holographic duals of this 11-dimensional solution, but I don't really know much more. I don't really have anything more to say about that. I just comment about it because I think this is an interesting link to some deformations, and it's intriguing the way that it's mapped to the new solution. You can be a bit more general. You can show in my most recent paper, you can show that if I start off with some initial solution with has two commuting isometries to which you can do honest U-dualities. These get turned into these funny non-isometric U-dualities of the 11D solution, which for this particular case of TST transformations give you these six vector parameters, where the sixth vector somehow is involving both commuting killing vectors as well as directions which are not killing, but which are linked, very much linked to the Poisson-Lie symmetries underlying the construction. So I come to my conclusions just in time. I think that generalized U-duality has some potential as a way to find interesting supergravity solutions. The inspiration comes from generalized T-duality, thinking about how it uplifts to M theory. And it certainly gives you a supergravity solution generating mechanism. Whether duality is too strong a word for it is maybe a different discussion, but I think it's interesting to try to explore this beyond beyond individual examples. If you go to higher dimensions, higher rank U-duality groups, you have more n-vector parameters. You have things like the six vectors. You can study similar ansatses in those cases. And briefly at the end, I mentioned that we saw in our solution these non-trivial deformations, which are U-dualities acting not just along isometry directions, but also along directions associated with these Poisson-Lie symmetry structures, where you don't have isometries, but you see instead these dual n-algebra structure constants appearing. So that's possibly some interesting direction to go, some new possible class of deformations with some nice algebraic interpretation. So thank you for listening. I hope this was technically audible, and then hopefully I'll see you next time.
Yes, Chris, thank you very much for the nice talk. So are there any questions from the people here in the audience? Yes. I'm sorry.
Okay. Is it possible to take some non-relativistic limit of U-duality? Could you?
As in a U-duality of a non-relativistic background?
Yeah, I mean, I know there is T-duality in non-relativistic sense, so I mean.
Yeah. Yes, you can do that. So in fact, it's convenient to use again exceptional geometry sort of techniques there. Yeah, you can describe some sort of membrane. So in the T-duality case, you have these stringy Newton-Cartan limits, which give non-relativistic backgrounds adapted to strings, and there are membrane and other brane versions of those, and you can dualize those, and some of the dualities will take you back to a relativistic theory, and others won't. I do have expressions of this form in some of my papers unrelated to this talk, actually.
Okay, thank you so much.
Okay, any further questions? I don't see any, so then let's, you?
Hi, Chris, this is Sibylla speaking. Hey.
Hi.
Just, it's not really a question, I think more just to clarify. So, did I understand correctly that for this Poisson-Lie U-duality to work, you had to, so if you can you go back to the exceptional Dreamfield algebra? So this first commutational relation on the T with a lower index, you had to channelize that to, well, so that you have not a subalgebra anymore, so you have an extra term there?
Yeah, basically a flux.
And the U-duality transformation, how is it acting at the level of this exceptional Dreamfield algebra then? So I cannot see it anymore as a swapping of subalgebras.
Yeah, no, it's a swapping of a subset of generators, but not between a subalgebra and a subalgebra. There would still be an action of SL5 transformation on the generators that would take you to the new set that you want to identify as your physical for, but then they just wouldn't be a subalgebra.
So
But
it's like
I think I do know what the transformation is.
so it's like scrambling the T with one index with the T with two indices, or
Yeah, it's probably you need to do some additional decomposition, and then you take some of the you take a few of the T's, take 3 of the T tildes and 1 of the T, and say they're my new isotropic subset. Yeah, so you need to choose an isotropic set of generators with respect to a certain notion of isotropic. And you can realize that by a transformation, and you can do that for many cases. Just what you want to get at the end is you want to get something you can go back and write down the generalized frame for. And if you have a subalgebra, this construction, you immediately know what the generalized frame is. But then if it's something where it's not a subalgebra, you have some additional term on the right hand side, you need to modify it.
okay.
And we didn't need to. So there are generalized frames for this CSO gauging that we could have used, but there was also this older style presentation of the consistent truncation that we used. But in principle, I mean, you could also do this generalization in the context of possibly T-duality, that you could allow to choose an isotropic set of generators that's not a subalgebra. And then you just need to work a little bit harder to know what to write down to construct the background.
Mm-hmm. Okay, thank you.
More questions? Okay, when there are no questions, then let's thank again Chris.